All right, thank you everyone for coming. Let's get started. First, this presentation came from work that was done in a collaboration between Erlang Solutions and DNSimple around Q2 this year, more or less, Q1 to Q3, more or less Q2. Why this work started? DNSimple built their authoritative name server in Erlang. That's the main point of the whole code. It has been in production for many years. They have some really fancy clients. But there were some problems and that we had to fix. Before the whole work, there was a more or less biweekly incidence rate and a relatively limited query capacity. Like after the work, there has not been a single issue since June, more or less, May. And the queries per second right now are roughly around 72,000 queries per second in a geographically distributed cluster. And last time I checked, CPU usage was really boringly below 10%. I want some adrenaline. Anyway, so the agenda for today is a quick DNS introduction, just enough context so that we know what we are implementing and also that you learn a little bit about this thing that we all heard about. We all kind of know how it works, but nobody really bothered to check the details. And it's very critical. And then, the actual meat. What's DNS? You have heard probably something similar, the internet phone book. So you look up the IP address of some human-friendly names. This is how I usually explain to my mom or to my grandma that doesn't know the internet. You type google.com or whatever, and like computer doesn't know what is that. So it's a phone book address. But it's more complicated than just the IP version 4. There is a lot of stuff going on. It's critical to the function on the internet. Nothing works if this doesn't work. If your service cannot be found, then it's useless. It was designed for scalability and decentralization, but not with security in mind. The RFC from this, the first RFC defining DNS is from 1987. Back then, it was a bunch of happy universities. Nobody would imagine that the internet would become the evil place it is today. Every internet request goes through this. Every time you send an email, use ChatGPT, whatever your favorite thing. Kubernetes needs also DNS. Everything needs DNS. It's like electricity for the digital world. And DNS outages cost billions globally. This was very fun. I prepared this presentation some time ago, and then a couple of weeks I was just going through just to see if I need to update something. And by coincidence, at the moment I'm checking, then I just check the news, and AWS DNS is down. It's like, brilliant. Anyway, it's a hierarchical structure with certain global root servers and a bunch of top-level domains. What does it mean, these root servers and the hierarchical structure? Let's see it with an example. Let's find the IP address of codewineurope.com. We are going to remove some extra fancy stuff. We are not doing DNSSEC yet or no cookies. We just want to do the tracing. What happens is that around here, my computer asks my router, who is the domain, the server responsible for the dot at the top. So there is 13 root servers. In reality, it's more than them. There is some magic going on. It's not 13 machines. It's God knows how many hundreds. But they are fixed. This is the source of all truth. And one of them says that these are the servers that are going to tell me the answer for the top-level domain, for the .com. So you can see here that all the servers are responsible for the .com, top-level domain. So then my router chooses one of them. You can follow the IP addresses here at the bottom. And one of them says that these are the servers responsible for the codeeurope.com. So then my router chooses one of them and asks them, maybe you finally know. And that one says, OK, now yes, I do know. These are a bunch of different IP addresses for the codewinbureau.com. This step-by-step resolution, those servers are called authoritative. Recursive resolution is when a server does the whole recursion for you. So your router doesn't go all the round trees level by level. This can go very low in the hierarchy. There is a recursive router that has done this for you. Probably it has a cache value already, so it doesn't need to traverse the tree again. It can just respond it to you. Famous one is 1.1.1.1 from Cloudflare, or 8.8.8.8 from Google, and 4.4.4.4 from, I don't remember their name. There's a bunch of popular ones. Your router may do similar things. You probably have daemons in your computer doing similar things. That's very important difference between recursive and authoritative. So again, you query this time. I remove the tracing flag. I get a bunch of flags that recursion was desired and recursion was given. There was one query with 4 answers and 1 additional record. The additional record is some extension flags that says the size of the packet and doesn't use any other extension. And the answer, I have 4 of them, the same 4 than before. So the recursive handles the entire query for you. Security was an afterthought. Then the evil became what we'll know it is, and we needed to do something about it. There is a bunch of problems with this. All queries are plain text. So, and they are also not authenticated, not encrypted, and not, how do you say, they are not protected against, in-flight changing the values. So we need to do something about that. This is where DNSSEC comes from. It works with a chain of trust. This is going to be very similar to your usual TLS certificate chain of authority, but the chain is going to be the same servers that go one after another. It gives you authentication. It verifies that the response comes from the source that it says it comes from. And data integrity, this is the word, data integrity, so the payload has not been tampered on the fly. How it works, there is extra records that give signatures about the actual record you queried. It uses public keys, just like your usual TLS many of you might be familiar with, and it uses some extra record other than the record that says, I'm not responsible for this domain, but he is. Now there is a second one that says, and by the way, this is his keys. How does it work? Let's query a record that will respond me with the DNSSEC that I want. ecan.org, people responsible for setting all the standards. But this time I'm going to add the flag, DNSSEC, and in the answer, this time, has 2 records. Before I had 1, and the second record is this resource record signature that gives a signature about the A record. There are some challenges in this protocol. One of them is negative answer. The problem, how should negative answers be cached? You know, a positive answer says, okay, cache it for 1 day or a week or whatever, but a negative answer, like, there is a bunch of RFCs correcting another about how to do this better and better. And this is one of my favorites. DNSSEC requires signing records, but how do you sign something that doesn't exist? Like, you know, the cryptographic signature of an empty string, like, all the queries in the world that doesn't exist would theoretically return the same. You get the idea. So it gets very tricky. The solution to these things, the source of authority, which says I am the authority for this subtree of this massive tree, provides TTL for negative caching. And for the DNSSEC, there is 2 algorithms, NSEC and NSEC3. They have different trade-offs. NSEC3 is way, way more expensive. NSEC is a lot cheaper on the server, but it leaks data. So it's challenge. It's a big challenge. You sign the absence of a record by proving that you know what is the next record and the record before it, because the tree is order. And that way you prove that I'm the authority here and I know that there is nothing between these 2, but then you're leaking those 2. And if you want to hide them, you need to do a crazy lot of hashing, which is very expensive. At scale is crazy. Another challenge, emptying on terminals. So what if a.example.com exists and c.b.a.example.com exists? What is the status of b.a.example.com? So there is also a bunch of RFCs, one correcting the previous one, because this is never clear enough. The idea is that it does exist, so the answer of the query is not going to be an X domain, which means non-existent. It's going to be cool, but with no data. So it provides another bunch of challenges. And as I said before, DNSSEC complexity, signing empty binaries is a big deal. That's more or less all you need to know. If you want to learn more, you can check these resources, a couple of very funny comics created by DNSimple about how DNS works and how DNSSEC works, and a book by Andrea Lopardi. He was presenting earlier before the Elixir update. He published a book some time ago, not long, about network programming in Elixir, and there is a part of the book where he deals with the library that we are just going to present a little bit, and with network and some challenges that DNS may face. Okay, that's all you need to know for now. How long it took? 13 minutes, perfect. Now let's get to Erlang code. How this is all implemented? It's in this record, in this repo. But for transparency, if you're watching this in YouTube, hello there, in 10 years, it may have changed. This is version 8. 9 is going to be released soon. Didn't change so much so far. But you know, the future. So for the record, it's there. And the first question that may arise is, why implementing this in Erlang? First of all, because OTP. Let me give you a textbook example of OTP stuff. So the application starts with a top supervisor, DNS sup, that has a strategy REST for one. Ingela was mentioning yesterday that she doesn't know an example. Here's one. That has 3 hierarchies. To the very left is another supervisor that will deal with workers that deal with ATS tables, handling all the zones. If that one dies, I have nothing to resolve. Everything else doesn't make sense. I can stop the UDP listener. It's pointless. The next supervisor is regarding the actual resolution algorithm. If that one dies, again, I don't need the listener, but I don't need to restart the ATS tables. The ATS tables can contain like 20 gigabytes of memory in a very small case. I don't want to populate them again, really. It takes a while. So don't need to kill them. And likewise, if the listener dies, the whole system is fine. You just need to restart the socket. Let's go from the right. What do? Listeners, I have TCP and UDP listeners, and an extra super fancy thing, a scheduler monitor. Did you know that DNS, 25% of the DDoS attacks in the world are attacks to DNS? And it's a funny one. Like if you go to the dark web and you go to your favorite provider, favorite lookup tool, you still learn something and you type, I want to be an evil hacker. Where do I start? The first thing is attack DNS. That's like one-on-one for evil hackers. Ask me later some ideas about like how to attack DNS. I don't want to explain it here, but it's really fun. It's an amazing topic. It's incredible. Anyway, so this scheduler monitor, it's a process that is working on a clockwork. Credit, this was an idea from WhatsApp. There is this presentation from Codebeam America from last year, where this guy gave a lot of internal things that were going in WhatsApp, and there was one idea that I thought, hey, let's try that one. He didn't provide the code, but he said in a nutshell how it works, so I said I'm going to implement this. So there is a timeout. By default, if I remember correctly, it's every second, but you can configure it. And every second, there is a worker that gets the timeout, starts another timeout, just to check again the next second, gets the scheduler wall time, which is using Erlang statistics, and is having a look only at schedulers online, doing some arithmetic just to calculate the average utilization, ends up with a percentage value with 2 decimal points, but then I multiply by 100 just to keep an integer and not a float. So you would see here this 10,000. So I'm just moving the comma, and I put this in a global atomic. Then the listeners, when they are getting packets from the TCP and the UDP socket, they get a bunch of packets and act on them, and then before taking more packets, they get the total scheduler utilization. If the scheduler is less than 90%, or if it's more than 90%, but I'm magically allowed to continue, just continue, just set the socket as active and get more packets and do more resolution. But if that logic returns true, that the utilization is above 90%, then I run some telemetry stuff used for instrumentation, and I will just not take more packets. I'm going to check again in a second. This maybe continue. Oh, here. The maybe continue. How it works is that if utilization is 92%, we have a 20% chance of not taking the next payload. Some arithmetic rand uniform between 1 to 0, and then do the aggregation. So the probability that rand is going to return what I want is works like this. More arithmetic. Never mind. If utilization is 96.23, then I have a 62.3 chance of not continuing. So basically, this is going to prevent the machine from overwatering itself. There is a chance that the network card is way faster than the CPU, and more packets can arrive through a 10 gigabit cable than the CPU is actually capable of ever processing. And this may happen. So if I know that my CPU is at 100% and the network card is insane, I'm just going to drop packets. It's better to do that than to waterlog the whole machine, explode memory, everything goes low, and then eventually dies. It's kind of a brownout. I will still serve very well a lot of the queries to a really big capacity. So now, listeners, easy one, the TCP is the less popular, but it's using Ranch. So because popular Erlang TCP socket library with a bunch of configuration. So I say Ranch, many of you would be familiar with this. It has some alarms when there is way too many connections or they start taking too long. In DNS, usually if a query takes too long, the protocol considers that it probably time out, just try again. So it's a hard requirement. There is a number of acceptors for parallelism, a maximum of connections that I'm going to accept. On the scheduler, there was another talk on how the schedulers work, and the scheduler has a queue. If you put way too many workers, by the time you act on the last worker, probably the payload already time out. So you don't want a queue of 1 million workers. So I'm also just putting a maximum of workers that I will handle here. UDP works very similar, but handmade. So again, I have an acceptor pool that is listening to the socket, and I have a bunch of workers. This one is using worker pool. Brujo mentioned this library yesterday. It's using worker pool, and it has very similar configuration than the Ranch one, with like some strategies, some alarms, etc., etc. Both of them, the UDP and the TCP, are going to work very similar. The payload arrives. This case is for UDP. TCP, different tuple structure. I get a monotonic time, so I know when the whole thing started. Prepare the payload, send it to one of the workers. In the case of TCP, it just goes to a Ranch Pong worker. Both the TCP and the UDP workers are going to look then very similar. They get the payload, and they will handle it if it's still within time. So you have the time of when the socket took this payload, but I may be acting on this payload way too late. I may just drop it if already too long passed. If everything is fine, usual telemetry pattern, you may be familiar. Start, stop, error. If there is an exception, it's just a wrapper. Let's go to the meat. Decode. It's a binary payload, and I have to create a data structure. Run some pipeline. More on this in a second. Encode the answer. Send it back. So this is the meat of the algorithm. Decode, pipeline, encode, and send back. Why Erlang again? Anthony, CEO of DN Simple, he said that like his feeling when he started playing with this many years ago was he felt like Erlang was created to parse network packets. The DNS specification draws the packets like this, and it feels like you could just do binary pattern matching and a one-on-one translation on the RFC definition. It's amazing. If you have a look at libraries like the usual HTTP server, so Cowboy and Bandit, I have not checked the Glim one, the source code, but I'm pretty sure it's going to be very similar. You do binary pattern matching on the structure of the payload and create your data structure, and it's just incredibly easy to write this code. So we saw the listeners and the parsing, decoding works very similar. Let's go to this pipeline. Pipeline has a bunch of workers. Never mind, look the code. There is a very important one. That is this one that is responsible for registering pipes in the pipeline. What's this? Pushman plug. I just like, I'm an old school Erlang person, and I was for a while skeptical about Elixir. Before Elixir, I did a lot of C++, and metaprogramming in C++ was my worst nightmare. So when I heard that Elixir has metaprogramming, I was like, oh God, no, again, metaprogramming. Until, honestly, I read Plug's code. Then I love metaprogramming. This is amazing. But I don't have metaprogramming in Erlang, so it's just a poor man's plug. I don't have also a million other features. I'm going to focus on just like one little task, DNS resolution. How does it work? At configuration, because again, I don't have metaprogramming to do this at compile time, so at configuration, I get a list of pipes from the environment. I prepare them and put them in a persistent term for performance. What preparation looks like. Important thing is this: ensure the code is loaded, it exists, and I can use it. Too fast. Ensure that the function call is exported, and maybe the prepare one also is. If the call is exported, just put the function object. Read the Erlang efficiency guides. Like, there is like a lot of details. I know the efficiency guides by heart. Like, I read them like for breakfast. There is a lot of stuff going on here. If the prepare is also available, I'm going to run this. This is what the plug would run again at compile time. But I don't have that magic. I didn't want to do parse transforms yet. They are evil, as we heard in a different talk. So for the future, maybe. And if the prepare call is available, I just run the call to extend the options. And again, why Erlang? Functional approach. It makes this whole thing super easy. You'll see how easy. You remember the encode call pipeline, the code pipeline encode send back. So the pipeline is going to do that thing, gets the pipeline with the DNS message and some options, and I'm going to start running the functions one by one. The functions may return hold, and then I'm not going to encode and return any answer for whatever reason. For example, the DNS, like DDoS protection or whatever, I decide to ignore this payload. It may return a new message, and then I'm going to call the next pipe with a new message. This is what plug does. It may return a new message with more options or an extended accumulator. So then I would just going to call the next pipe spot with a new message and the new options. It may return stop with a new message, and then I'm not going to call the following pipes. I'm going to stop here, and this is the message that I'm going to return to the worker to encode and send back. Usual telemetry, there is some, like in case there is an error, some exception handling, and then just call the next pipe. And your default pipes look like this. First of all, questions one. In DNS, it is possible to ask more than one question, but the answer only has one status. So it's pointless to make two questions, because if, you know, the two questions may have a different result. So nobody really asks two questions. Nobody does it. And you usually could consider if somebody is sending you a query with more than two questions, he's actually probably trying to waste your CPU to parse that. It's probably pointless. So again, like if the query has more than one question, I may drop all the others or drop the whole thing. Then I'm going to ensure the maximum payload size, because UDP, unlike TCP, UDP does not implement partitioning the payload if it's too big. That would be done on the IP layer, and network providers would hate you for forcing them to do IP partitioning of packets, because it's expensive on the routers, not on your computer. So they usually just drop this. So you don't want to partition on the IP level. So if the payload is too big, you need to cap it, drop it. So I'm just ensuring some maximums here if this is running over UDP. I'm going to run some throttle. If there is an IP address that is querying me too fast, then again, I can return halt or error. I may cache. This, again, I didn't have metaprogramming, so I had to do a bit of like dirty magic here. So the cache runs before and after resolution. If the one before had the answer return, if it didn't have, continue. And then after the resolution, just take it and put it, and the message doesn't change. Then there is a recursive resolution. In this implementation, this is a stub. It's just setting the flag that I don't support recursion. It's not implemented yet. Because we're focusing authoritative, and most of the magic is here. Run the whole authoritative algorithm. If DNSSEC is enabled, append all these error signature records. Sort the answers. Run some metrics. So this is just going to take the payload and spawn a bunch of telemetry events. And verification, if the answer is empty, I also want to do some other DDoS protection or magic, metrics, so many things. If you want to do more stuff, just, that's why it's functional. It's easy. Just put another pipe somewhere in the middle. Like new RFCs with new extensions, correcting the previous one, just put another pipe here. And now to the left, the last part of the supervision tree, there is the ERL DNS zones. Which, again, REST for one. To the very left is a Gen server that owns a bunch of ETS tables. If this dies, everything else it's pointless. The ETS table was 20 gigas. It's going to take a while to repopulate. So this is to the very left of the very left. And then there is some codecs and loaders. Zone management architecture. This is also read the efficiency guides and ETS table like efficiency guides. There is so many stuff going on. ETS based for fast lookups. It also supports encoding and decoding of some data formats if you have some custom records or new records that are private. So this repo is open source, but it is used as a dependency in a bigger application that does more stuff. And also a loader. So at startup, you can, at the moment, load from JSON files, and it's doing all this magic in parallel, so you can populate your tables as fast as possible. This reminds me, I remember when I implemented the parallel loading, and you want to load 20 gigabytes of data. It was like on a single threaded, and it was taking like half an hour. Then it takes like 2 minutes. Still 2 minutes is a lot, but hey, progress. The zone table, that's the meat of this whole thing. It has 2 important tables. So the zone worker has 2 important tables. The zones table that stores metadata, so the DNSSEC keys. Usually you pre-sign your records while you populate the table, so you don't need to calculate cryptographic stuff at runtime. You just pre-sign everything. But negative answers. How do you pre-sign all the negative answers in the world? No way. So that one you have to calculate it at runtime. So the keys are there. And then some versions, authority, the record count, some metadata about the zone. And the fun table, this one is an order set, because the implementation, again, read all the guides, so much stuff going on. The implementation is a tree, which is just like the DNS hierarchy tree. It's perfect. It's exactly what we needed here. The key is a triplet with 3 elements, the zone labels, the subdomain labels, and the type, so A records, or there's just so many of them. So if the zone is example.com and the domain is A1, A2, example.com, and the records are of type A, then my key looks like this. So I am partitioning the subdomain from the zone, because the zone is authoritative for this domain. So if there was a query, for example, A3, A2, A1, that wouldn't return an answer, then I can start traversing up the tree just to know if any parent exists, up to the zone. Like if I arrive to the zone, I should not traverse higher up. It's in a different place. It's in a different zone. So that's why I'm only storing here the sublabels and in a reverse order. You're going to see the trick in a second. So when I'm looking up for a record, I first start with the zone. So given a domain, I just partition in a list of all the elements in the domain. I do some ETS lookup on the first table. It returns the zone. Then I can use it. This has 2 clauses, but let's focus on the second. The first one is just splitting the binary into the labels and calling the second. So let's imagine that we already have the labels. I'm going to take out the labels that belong to the zone from the domain, so I don't traverse too much, too high. And this is going to be my query. So the zone labels, record labels, and type. Because this is an order tree, the type could actually be It could be wildcard. And then I'm not going to traverse the whole ETS table. This is an order set ETS table. So ETS knows how to do prefix lookups. And it's just going to traverse the tree first on the zone labels, then on the domain labels, then on the type. So I can do all these wildcards. And also, even on the labels, imagine that A2, A1 didn't exist. Then I can just put a wildcard at the end. Or even more fun, this is super fun, I can just put not a DNS wildcard, but an ETS table wildcard. And this is very important. It needs to be an improper list. So if you see, I'm not appending a list that contains the wildcard. I'm appending the wildcard. So this is an improper list. Why? Because the ETS table is going to then tell me if this domain has any children whatsoever. And that's how I resolve the empty non-terminals. You know, the C, B, A exists, A exists, what about B? So with this, I can just put to B, append the wildcard in an improper list, and the ETS table is going to tell me in an amazing speed if there is any children whatsoever. And then I know, empty non-terminal. To end up a little bit, codec is just converting between internal and external representation. The internal representation are records with types. External representations, there are many of them. We use JSON mostly with custom codecs. The parallel zone loading is by default taking all your JSON files from this directory. And it supports parsing extra records. And to recap, the whole pipeline works like this. You start with the JSON files, load them in parallel, run some extra codecs, put them in the ETS table. Then your TCP/UDP listeners are going to run through workers that will handle the requests, decode using the wire format, which is amazing, the pipeline resolution, poor man's plug, encode back to the wire format and put it back to the socket. And with this, how are we doing with time? Very nice. Just a small recap, what is the future? Feel free to ask me more questions about these things. Mostly DNSSEC adoption. If you read adoption statistics, they are sadly low for a lot of domains. But for some of them are strictly required. .bank, for example. I learned this yesterday. Thank you. .bank requires DNSSEC. In reality, like in my heart, all of them should require DNSSEC, so we're going to work in having better support and with all the performance challenges that brings, unfortunately, but the world is an evil place, so you have to try your best. And then operability. DNS, a lot of complaints are about how hard it is to maintain this stuff, how backend-ish, this is like the backends of all backends. Nobody knows how this works, so supervision trees are documented recovery. It's kind of like self-readable. You understand how it works if you know the strategies. REST for one, my favorite. More comprehensive introspection. We want to add more data gathering. For business analytics, also to know what are the most popular records, what like to calculate our own statistics about the usage of different features. And with that, that's all. Thank you very much.
That's amazing, Nelson. Do we have some questions here?
Thanks for a great walkthrough over DNS and implementation. I have a question on one of the earlier slides. You had a worker called aggressive queries, and obviously that drew my attention. On the other hand, you didn't want to discuss all of that.
Which slide?
The one having the supervision tree and workers. It was like 10th slide, maybe.
On the pipeline, on the supervisor?
No, earlier.
Earlier. This is the first one?
Yeah. You had the one listing workers.
The listeners, you mentioned?
No, workers.
Which one is the workers? Let me see. There was...
I'm just curious what an aggressive query looks like.
An aggressive query. There was also this one on the pipeline. So there are some workers on cache. This one, aggressive queries. One. Perfect. The throttle. For example, there is a any type. So you can make a query not for the A records, which is the usual one, the IPv4, but you can make a query for the any. type, which means give me all the records for this domain, which can be a lot of them. Maybe this domain has a lot of the 4As, so for IPv6. It has some C names, a lot of DNS signatures, a lot of stuff. And the problem is amplification. This is why it's so fun to attack DNS, because the query, the payload, the wire encrypted for give me the any for example.com is around 40 bytes. But if the answer is very big, the answer could be several kilobytes. So the amplification is brutal. So any queries to any are like a bit weird. Like I want to throttle those or stop them altogether. That's an example. And then I can also do, like, if there is an IP address that is just querying random stuff at a speed of light, then also, yeah, okay, stop. Like, things like that.
Thank you. Another question over there.
Hi. Really interesting. Thanks a lot. Haven't seen anything about Napter or SRV. Does it support Napter records, SRV
Yes.
records? Okay.
As far as I remember, yes, both of them.
Okay. Okay.
There is just way so many records that I just mentioned. A records is the classic one, just for simplicity.
Fantastic talk. Thank you very much. Really enjoyed it. Why are the poor man's plugs stored in the application environment rather than being hard-coded?
You probably mean this slide is going to be pipeline is here. That place, right?
Yes, that one.
There is a default one that is the macro, but you may want to configure, we do that in the parent application that does some extra private stuff, extra plugs. And it was the simplest way. Like you just configure it and you can put extra pipes on a given order, usually metrics or custom records, things like that. Do you have any better way to do this without metaprogramming?
No. I was just wondering if you changed them a lot or something like that.
You just, like, on the sysconfig, you just put, Erlang DNS, packet pipeline, and a list of modules. And then at startup, I'm going to check that the modules exist and export all the expected callbacks, etc.
Great, thank you very much.
There also, I forgot to mention for the people online, you can use swap card, and we actually got an online question, so I want to read that here. From Piotr Nosek, he asks, traffic throttling by scheduler usage seems like something that should be a standard practice for many other online apps. Have you explored if there's a library that already does it, or does DNS Simple intend to wrap this pattern in a dedicated library?
Amazing question. I did thought the same. Why is this not more popular? And I could not find any public library doing it. I was very happy to see the presentation from WhatsApp, but it's internal code. The presenter was saying this is how we do it. So I went the usual way. I implemented in the place that I needed, and after a while, if it's useful and if it's stable, and then it can be extracted into its own library. Sounds like a very universal pattern.
Yeah.
Thanks. So obviously, I was in a privileged position to see this evolution of the CTO at DNS Simple. So we worked together to evolve this product. One of the questions I have is, what was your most favorite change of all these months working on this application?
Okay, so there is all the, read the efficiency guide. It's my daily breakfast. It's amazing. There is like a lot of crazy stuff going on. All the tiny details about encoding, decoding, parsing, optimizing the function. It's so much fun. But a couple of things that I like very much was this whole ETS trick to resolve the empty non-terminals. I loved it. It's just so simple. Like, this is also the only use case, the only reasonable use case I know of improper lists. It's perfect. This is what it's for. But really, my favorite thing is the pipes. Like, as I said before, I was skeptical about the Elixir and metaprogramming from C++ until I discovered Plug, and I was like, oh my, that's what I want. So trying to imitate at least the pieces of Plug that I need was also a lot of fun implementing, and it gave me a lot of power to then add new functionality. For example, we had way worse metrics before. So once I have the pipe, I can just put some of these extra pipes, just read the packet and put metrics. It's super easy. And then adding custom behavior in the parent application, super easy. It was very fun to do this part and very functional.
Thank you so much, Nelson. Please.